this talk is loosely themed after one of them, and I've got some videos in here, hopefully to kind of liven things up, keep you awake, and provide some comic relief. If you don't already know which movie this is themed after, you're probably going to find the video clips a lot less amusing than I have. So some quick notes on mitigation. I use this term because in VoIP, many times there's cut solutions to any particular vulner attack. And sometimes the best we can do is lessen the severity of the impact or the threat. Because of the design goals of most VoIP systems and protocols, it includes global connectivity between devices. So, and it also includes convergence with other types of communications mediums like IM, email, and customer relation applications. So due to that, I'm not going to be touting the solution of just isolate your VoIP network from your data network or from the internet to protect it. One of the things that they're trying to do is converge with all of these other things. So they're essentially going to have to talk to the data network at some point. I think that isolating your networks essentially a short-term solution, and I don't like those at all. Also, mitigation techniques that I'm going to suggest actually do work fairly well. In the third section, I'm only going to be discussing those that don't, or those that have some serious drawbacks. All right, so here's the part where I attempt to cover my ass and say that all of these clips are copyright Warner Brothers, at least all the video clips. All right, so first, some quick VoIP basics. So basic terminology, obviously VoIP is Voice over Internet Protocol. A call is basically the session aggregate of signaling and media. An endpoint is where a call terminates. Soft phone is usually a VoIP phone implemented entirely in software. And a hard phone is a VoIP phone with a physical presence like that would be sitting at your office. Key thing to remember is in VoIP, there's usually separate channels for your signaling and your media. So this is kind of a design convention that has been adopted from traditional telephony systems. Because back in the day, blue boxes, red boxes, things like that, basically sent the signaling over the media channel, and the remote devices would pick up on this signal. That was due to the combined channel being both signaling and media. So that's kind of the way things have gone in VoIP as well. But there are some protocols like inter-asterisk exchange that kind of combines the two into a single channel. Although that's a little bit misleading because within that channel, they're still separate by like different message types because it's basically a data protocol. So some VoIP services that you might want to keep in mind is call control service is what basically sets up calls, tear down calls, changes call parameters during mid-call, things like that. Directory service is what looks up and maps usernames, phone numbers, things like that to phone extensions and transport addresses, so it knows where to send the call. Gateway handles interactions between different types of networks. Network services, usually when you're talking about in VoIP, kind of mean the underlying network services like DNS, FTP, DHCP, all of your traditional network services. And session border controllers are kind of a specialized gateway, but they're intended to be handling traffic that crosses a trust boundary of some kind. These are the kinds of devices you would put at the edge of your network to connect to the internet or to route calls out going to other entities. So some protocols and ports. Session initiation protocol is a big one. It's grown quite a bit over the last few years. Session description protocol essentially runs within that and describes the session. SIP handles setting up the session. Session description protocol handles coordinating the parameters of the session. You also have Media Gateway Control Protocol, Skinny Client Control Protocol, which is Cisco's proprietary signaling. Real-time Transfer Control Protocol, which is essentially your signaling specifically for the media channel. And then you have your media protocols, which right now most things use RTP or SRTP. And then, like I mentioned earlier, you've got hybrid protocols. One that wasn't on that slide because it won't fit with everything else is H323. It's basically a protocol suite. It's got a lot of different signaling protocols in it, and it also uses RTP for the media. Some audio codecs. You don't need to know all of these. Basically, what you need to take away from this slide is there's a lot of them, and different devices support different codecs. Which one to use for the media channel is usually negotiated between devices in like the session protocol that I mentioned earlier. Finally, for the VoIP basics part, some architectures. You have an architecture which is referred to as intelligent endpoint. That basically means that all of the, or most of the logic is in the user agent device, the endpoint device. It knows how to forward calls, it knows what to do when it receives a call, all of that kind of stuff. It has its own dial plan. And some examples, H323 and SIP. You also have a device control architecture, which basically means the phone is dumb. It doesn't do anything unless the call server tells it to. If you pick up the phone and you press the number 2, it tells the call server that you press the number 2, and the call server then tells the phone, okay, play the DTMF for number 2. It doesn't even play the DTMF for you unless the call server tells it to. You've also got some peer-to-peer architectures. Right now there's not a whole lot of real true peer-to-peer VoIP architectures, but there's a couple being worked on. And then again, you've got hybrid mixed of all of the above. All right, so without further ado, I'll go on to the attacks. First, I'm going to talk about attacks against availability or denial of service attacks. And I think I have to turn some volume up. All right, hopefully you can hear this. Okay, maybe I got it a little too loud, but but yeah, basically, I don't know if you caught that, but they were blowing up Congress. I swear I've seen this movie probably at least 60 times in the last month, and it's still hilarious. So the first attack I'm going to talk about is device flooding, and I'm going to turn this down just a little. Okay, let's try this. All right, flood of Martians. Okay, so first, most hard phones are still relatively expensive to produce. Because of this, they're made as cheaply as possible and with just enough processing power to really do the job. Also, due to the nature of VoIP services, certain functionality has to be available to unknown and unauthenticated parties. To perform a flood attack against a VoIP system, two general methods are available. You can either flood the device with VoIP protocol messages like SIP invite, SIP options, register. Those are all good. Also, if you can identify the open RTP ports, you can start flooding the media channel with RTP packets. That's run over UDP, so it's completely essentially stateless there. Or you can flood the device with network packets like your traditional SYN floods, things like that. The effect of flood attacks usually results in degraded call quality or jittery or choppy audio. Or the device will crash or otherwise respond poorly. Keep in mind that excuse me. Keep in mind that because VoIP is essentially a suite of media applications running over a data network, most attacks against the data network are also applicable. Voice is particularly affected by latency and quality of service issues. So, you know, my manager at Tipping Point recently wrote a book on hacking VoIP, and they created a bunch of tools. So luckily, I didn't have to recreate too many of these for this talk. But basically, your general purpose packet tool can do your network type floods, like your SYN attacks, things like that. How did that happen? All right. You also have some special purpose VoIP tools like invite flood, IAX flood, UDP flood, RTP flood, those types of things. You can go grab any of those and play with those. And to protect against your basic flood attacks, you can protect your core VoIP network from external access, like firewalls, session border controllers, strict ACLs. You can also rate limit offensive traffic at similar points of control. I know I said at the beginning that I wouldn't use the so isolate your network solution, but in this case I'm referring to the network layer, not necessarily the VoIP services themselves. All right, so next I'm going to talk about fuzzing. I'm not going to talk too much about this because it's been talked about a lot over the past 2.5, 3 years at various conferences. Basically, like I said earlier, VoIP is in its relative infancy. Protocol stacks are simply poorly implemented and they're fairly immature. While core devices and servers tend to be a little more resilient to this type of thing, many of them use the same protocol stacks as the endpoint if they're from the same vendor. If it's going to affect the endpoint device, it'll probably affect the server as well. So basically, you fuzz the devices and you find the bugs, and that's just fuzzing. So some tools, some specifically SIP fuzzing tools is the Protoss suite. It'll fuzz SIP. There's also one for HTTP and SNMP, which are frequently used within VoIP architectures. There's an RTP-specific one called Ohrworm. There's a fuzzy packet, which is a RTP fuzzer, which has a built-in ARP poisoner. So if you're doing any of those types of layer 2 attacks, that is built in. And then there's just a ton of other tools. There's this wiki here, which will probably be touched on in the fuzzing talk here at Toorcon also. There's a few ways to help mitigate against fuzzing. First, you can use open source soft phones and hard phone firmware, because at least then you can look at it yourself. You can see if it's got issues. If you find the issues, you can hopefully report them to the maintainers and have them fixed relatively quickly. If you use a specific vendor, you can demand resilient devices from them. I don't know how well that will work, but you can try. You can also ask them about their QA processes. Maybe if they're getting asked more frequently, they'll realize it's in their best interest as a business to start building these types of things with more resilient stacks. Next, I'm going to talk about amplification attacks. So yeah, giant robots are cool. Because many protocols provide unauthenticated functionality to unknown parties, and many of these protocols use a connectionless transport, it makes it quite trivial to spoof the source address of your packets as your victim and have multiple devices that are receiving those packets respond directly to them. Invoking functionality that responds with a much is your basic amplification attack. And you'd think we would have learned from the Smurf attacks, and apparently not, because just recently there were some attacks that I had actually in my talk specifically for Asterisk, but have recently been patched already, so go open source there. So some tools, pretty much any packaging tool can do this. You can build your own for more specific protocols, or you can modify things like Scapy, add your own protocols there. But there's a few ways to prevent against this. First of all, if the protocol supports multiple transports, use a connection-oriented one. That way, it's a little more difficult to do. Also, authenticate as many protocol messages as possible. A lot of these protocols may authenticate you at the beginning, and they don't after that. The individual packets coming in are not all authenticated. And finally, you can rate limit your network traffic at points of control, kind of like I mentioned earlier. So my next one is called forced call teardown.
I've been trying to call you all day. The flight's been canceled.
Byron, there's Martians everywhere.
Hello?
Byron! Byron!
Yeah, so the worst time to have your call torn down is when there's Martians attacking. It's not a good time to have the phone go out. So, the vulnerability here is that most VoIP protocols are unencrypted on the wire and don't authenticate all of the messages, like I said a second ago. Because of this, the signaling channel can be monitored and call state can be tracked. In order to attack this, you inject your spoofed call teardown message into the signaling channel, and it tears down the call in progress. Some effective messages for SIP are buy. There's a message actually called buy which tears down the call. Skinny has one called reset, and IAX has one called hang up. Basically, when this attack is successful, the target endpoint of the call thinks that the remote device has sent it the message to terminate the call, so it goes ahead and does so, and it essentially ends the call prematurely. There's a couple of different tools that can perform this attack. Teardown is a SIP buy message injector. SIP kill is also a SIP buy message injector, but it also supports injecting other types of SIP messages that will do essentially the same thing. And SIP proxy kill is basically a modified version of SIP kill, but it's to target specifically proxies. So some ways to prevent against this are obviously encrypting your signaling channel. And also, if you're not encrypting your signaling channel, authenticate all your signaling messages again. If it's related to an established call, you really should authenticate every message. So the next section is basically attacks against integrity. The first one is kind of a more generalized version of the one I just talked about, which is signaling manipulation. The forced call teardown was basically the same thing, but there's a lot of other things you can do with manipulating the signaling. There we go. So that one's kind of hard to catch, but the Martian in the middle was walking a severed hand across the table by manipulating its electrical signals. All right, so signaling manipulation is a pretty large area of attacks. Like I said, there's a ton of things that you can do by manipulating various signaling. The vulnerabilities here are, again, VoIP signaling protocols are unencrypted on the wire, and you can have unauthenticated functionality. So unlike traditional telephony, most signaling extends all the way to the endpoint device. This provides great attractive input vector for attacking. To perform signaling manipulation, you can do things like inject malicious signaling messages into an existing signaling channel between devices. You can also send new signaling message that are completely unrelated to call to endpoint devices or servers, things like that. You can forcibly tear call like we saw earlier, that attack was, like I said, really both an availability attack and an integrity attack. And you can also do things like cause the media channel to be redirected, duplicated, and sent to a third party, completely torn down. You can do all kinds of things with this. So this funny little diagram here is my attempt at diagrams for the conference. And this is commonly called the VOIP trapezoid. You'll hear that a lot if you start getting into VOIP. Basically, you've got essentially up at the top your call servers. The little phones there are the endpoint devices. They might not actually be phones. They could be an application running on your computer. But basically, the endpoint devices perform signaling with the servers up at the top. I'm going to use SIP as an example, so those are proxies up at the top. SIP uses a message called invite to initiate a session. So whichever one's initiating sends the invite up to its server. It looks up, figures out where to route the call, sends it over to that entity's call server, which then figures out, okay, this user, where is his phone? Where do I need to route this call? And routes it down to that phone. So for the simplicity, I'm going to assume that the two endpoint devices can route to each other directly. There's a lot of issues with NAT traversal and things like that. If you've got two endpoints that can't actually talk to each other directly for the media, but for the sake of simplicity, I'm going to assume they can. So you introduce the attacker, and what he does is sends signaling messages spoofed as the call servers to both endpoint devices, which requests them to redirect their RTP streams. With SIP, this is called a redirect. It's basically sending a new invite message that's associated with an existing call. So if this was done, completely outside of an existing call, it's how you initiate it. Once the call is established, you use the same message to basically renegotiate parameters like endpoint device addresses. If you want to change media codecs in the middle of a call, if you want to change the quality of service, things like that. So the attacker re-invites both endpoints and basically requests that both of them change the remote host address for the call to the attacker. So basically then the endpoints reestablish the media channels through the attacker, and he's essentially now an active man in the middle. And since VoIP people like to call their diagrams funny little names, I decided to call this the VoIP Pentagon of Power. So, all right, so some tools that are available to do this. There's one called SIP Redirect RTP, and another cool tool called RTP Proxy. You kind of use those together to do exactly the example that I just showed. SIP Redirect RTP will manipulate the signaling and tell the devices to send the media channel to the attacker, and then use RTP Proxy to proxy that data through, so that as far as nothing's happened. They're still receiving the media, the call's still progressing, everything's cool. So there's other things you can do with signaling manipulation. I mentioned sending new signaling to devices. One thing you can do with registration servers, which is, like I said in the VoIP basics section, what translates a user to an endpoint device. The device will register with that server and say, okay, I'm over here at this address. You can change that registration. You can delete the registration, add new registrations, and basically do things like hijack media, hijack entire calls, things like that through the registration server. And there's some tools to do that with right there. So some ways to protect against this is, obviously, again, you can encrypt your signaling channel. Also, the protocols should probably be fixed so that they authenticate all of the signaling messages. And like I said earlier, if signaling is part of an existing call and you already know the parties that are involved, you should authenticate those messages against those parties. So encrypting the signaling channel makes it much more difficult to monitor the current status of the call also, in which case you might not know what the call server addresses are, things like that. If you're the signaling in transit, almost all of this information is right there in the clear for you to read, and then do with whatever you may. So if protocols remain unencrypted, they should at the very least perform some form of authentication against the messages. I can't say it enough. So that's pretty much it for signaling manipulation. That's just kind of the tip of the iceberg for that one. There is so much more you can do with that, but it would take up hours and hours. So I'm going to go on to caller ID spoofing. And this one's also been talked about.
Don't run. We are your friends.
That's my favorite part of that movie. And luckily I found a way to use it. Alright, so caller ID spoofing. Probably right after eavesdropping the media channel, probably the most well-known VoIP attack. The vulnerabilities that allow you to do this are that most VoIP protocols are unauthorized and unverified end-to-end. Endpoint supplied data is not usually challenged in any way. Many automated systems also use caller ID information to authenticate users. So, you might be thinking that I'm oversimplifying, but I'm not. It's really easy to do this, and there's all sorts of things you can do with this. Also, there's many multiple outcomes you can achieve. First, you can obviously appear to the called party as someone you're not. You can use that, with phishing attacks, social engineering, all of that type of social aspects. You can also gain access control or gain access to automated systems like voicemail services, credit card activation systems. They usually authenticate you this way. You can, in some parts of the country, you can even pay your utility bills using your caller ID information to authenticate you. So in some part, something to keep in mind on the legality of this attack is right now it's not illegal in the US to spoof your caller ID. If you use that to access a computer system, obviously that's illegal. But in June, the U.S. House of Representatives approved a bill that would actually make it a crime to maliciously falsify your caller ID as it would be seen by the recipient of a call. So if that goes through, basically falsifying your information like this and then calling someone, a crime. So I think it's still being revised. I don't think it's made it through the Senate. I do not have it here. Yeah. Alright, so remember when I told you that this was easy? Almost all of the soft phones will let you set your caller ID information. It's basically expected functionality of a soft phone. There's also some VoIP service providers out there that will honor the caller ID information that you pass to them, which will then route your calls into the regular PSTN network. And there's one of them right there that if you want to use it. There's also some businesses that have kind of sprung up around this attack. Spoofcard.com will actually spoof your caller ID for you, and you don't even have to do it yourself. Oh yeah, what's the bill number? HR 5126. That's the caller ID bill. All right, so some thoughts on mitigation here. If you're service provider, don't use caller ID information to authenticate your users. It can obviously be faked. If you're a VoIP service provider, don't honor the caller ID information that's passed to you by your users. You know who they are because they're authenticating with your systems. Reset it to something legitimate for their account. And if you're a VoIP user, don't trust that caller ID information is accurate to identify who's calling you. It's just way too easy to fake. All right, so next we're going to talk about some confidentiality attacks. First, it's probably, like I said, the most well-known VoIP attack is called eavesdropping the media channel.
They're responding.
All right, so the problem here is that most VoIP systems currently use RTP, which is running under UDP and is normally unencrypted. Because of this, any third party along the media path can sniff the network traffic and reconstruct the media out of those packets and just put it into an audio file .wav whatever and then play it in Winamp or whatever. So obviously to perform this attack, all you have to do is be able to sniff and record the traffic. Format it correctly. Also note that within VoIP systems, signaling and media are usually separated. So if you can see the signaling and you can't see the media, you combine this with the signaling manipulation attacks earlier to redirect the media, and then you can see it. So at that point, you can redirect it, output it to a file and play it. So basically what all this means is that calls using RTP are not and can be eavesdropped. So here's a quick example using Wireshark. And this is a packet capture from the Wireshark wiki. It's an example packet capture. You can go grab it, load it in, and do exactly this example. Basically, there under the statistics menu is RTP and then show all streams. That'll analyze the packet capture and show you all of the RTP sessions. Next, you basically pick out which you want to look at and hit analyze. It then gives you this window where you hit save payload, and then it will prompt you there to decide what format you want to save it in and whether you want just that channel or if you also want its associated media channel going in the other direction, which you probably do if you want to hear the entire conversation. Otherwise, you'll just get one party. But that's literally how simple it is. So some tools. Obviously, I just showed you Ethereal Wireshark. There's also Kane Enable. Vomit is specifically for Cisco devices, and EtherPeak VX does something similar. And to mitigate it against this, obviously you want to encrypt your media channel. If your VoIP infrastructure supports SRTP, you should be using it. So the next attack is directory enumeration. It's basically a good way to identify users of a VoIP system, what extensions they can be reached at, where their devices are, that kind of stuff. First, many signaling protocols provide unauthenticated functionality. Sometimes they also respond differently to valid versus invalid usernames. And again, these tend to be unencrypted on the wire while all these transactions are taking place. So an active way to perform this attack is to send specially crafted messages to the registration server and see what you get back. With SIP, you can send options, invite, register, those types of things. And it kind of works much like the old SMTP verify command. You basically send it the username, and then you can tell whether that user is valid or not. You can also perform this attack passively, just watching the transactions on the wires. Like I said, most of them are unencrypted. If you just sit there and watch, you'll see usernames flying across the wire, going to the registration server saying, okay, this user is now at this device, or this user has changed to this device. So registration messages by definition contain that information. And obviously you can use this, this information in more targeted attacks against those specific users. So here's a quick example using SIP. If you send this options message to a SIP registration server, it will basically respond with, SIP's kind of like HTTP. It's got similar response codes. So if the user's not there, it'll respond with a 404 not found. If the user was there, you could expect something in the 200 range, which is SIP's success message range. So some interesting tools to do this. SIP-crack is passive. It'll actually sit there and sniff the network traffic for the usernames and then attempt to crack their passwords. Usually in the registration messages, there's a username and a hash. So at that point, it just sits there, collects it, and churns away on the hashes. A tool I recently wrote called enum.ix kind of does a similar thing against *IAX protocol. It sends a register request against the server and then listens for what's coming back. Interesting thing about IAX is it responds not only differently between valid and invalid usernames, it also responds differently whether that user has a password or does not. So not only can you tell if the user is valid, you can tell whether it requires a password to log in, or if you can just log in with the username and no password. Finally, a tool that David Endler wrote a few months ago called SIP-scan. It basically does the same thing as enum.ix against SIP servers. Uses SIP options, invite, and register. A lot of these VoIP protocols are just not securely designed. Not responding differently to valid versus invalid usernames is straight out of Authentication 101. You shouldn't do that. To prevent against these attacks, you have a few options. You can encrypt the signaling channel to prevent passive enumeration, and you can improve the protocols so that they don't respond differently to valid versus invalid usernames. All right, so now I'm going to talk about configuration disclosure attack against the infrastructure. I'm also going to talk about against the endpoint devices in a minute. So an interesting thing to note smartphones is that they use either TFTP or FTP to download their configuration file and their firmware image. That usually happens when they boot. TFTP is an insecure protocol. It doesn't require you to authenticate, and it's unencrypted on the wire. If you're using slightly better FTP, it's a little better because it requires authentication, but it's also unencrypted. To perform this attack, if the device is using FTP, first you need to sniff its login credentials. But because it's unencrypted, that's really not that difficult. If the device is using TFTP, you'll also need to sniff or guess the file names of its configuration and firmware that it's trying to receive. Once you've done that little bit of reconnaissance, you can basically grab the files directly from the file server, or you can just forego all that and reconstruct the files directly from the wire, since you're sitting there sniffing the traffic anyway. Obviously that requires that you somehow get the phone to perform this boot operation. But I'll talk about that in a few minutes. So you're probably wondering what all is contained in these files that would be useful information. There's usually usernames and passwords for authenticating network. There's lots of useful information about the VoIP network, such as call server addresses, gateways, registration servers, information you would need for some of the earlier attacks that I talked about. And there's usually some information about what services the VoIP network is providing to that device. Some phones that make use of TFTP are Cisco IP phones and 3Coms phones, while Polycom tends to use FTP from scene. Some tools to do this: obviously your packet sniffer again. You can use a little deductive reasoning for guessing file names. Usually Cisco phones have file names based on the MAC address of the device that's requesting them. So if you can see the device doing things and you know what its MAC address is, you can basically then tell exactly what file name it's going to go try to grab from the server. And if those files don't exist, which are usually there for specific configuration, there's also a set of defaults that it'll grab if those aren't there. Also, with Cisco phones, the firmware name, the name of the firmware file that they're going to be downloading is actually in the configuration file. So if you can grab the configuration file, you then know exactly what firmware it's going to go after. Also, see. So to mitigate against these risks, I mean, first you can see if there's an alternative to TFTP or FTP that you can use. And also try not to use default file names. If you can change those and have the devices grab them with customized file names, that would at least help prevent against the guessing. All right, so now I'm going to talk about kind of the same thing, except targeted at the endpoint device instead of the infrastructure. The problems here are that many hard phones provide information via HTTP, SNMP, and other management type protocols. Also, a lot of vendors even leave the VxWorks remote debugging port open on these devices, or at least a VxWorks console through Telnet or something like that. So to attack this, you can obviously try pointing a browser at it, SNMP walking it, or attaching a VxWorks debugger if the port's open. You can easily find out a lot of the same types of information that I talked about in the last attack, but there's also a lot of device internals you can get if VxWorks is available. You can look at RAM, you can do all sorts of things with the disk. So some tools here, obviously your favorite web browser, SNMP walk, or a VxWorks enabled debugger. And the best way to prevent against this type of stuff is to just lock down your endpoint devices. If you're not using the web management port, you're using management through the signaling, you don't need to have it open on your device. Okay, so I'm going to talk about a couple of vendor-specific attacks. You might recognize some of the elements I covered in the previous more generalized attacks section. But these should be specific to particular vendors. First, I'm going to talk about Cisco. So basically, here's your Cisco O-Day. Well, now it's 2004, so it's 2.5 years old, and it's still vulnerable. Basically, what happens is that Cisco IP phones run skinny for their signaling, which runs over TCP. TCP is vulnerable to a reset attack. If you forcibly close the phone's signaling connection with a spoofed reset packet, it performs a full device reboot. So this causes the device to go out to the TFTP server again, download its config, download its image file, all of that kind of stuff. And obviously the phone's not providing service while it's doing this, it's booting. So this behavior is current as of the most recent firmware, which was released about a month ago. This was disclosed by Cisco themselves in April of 2004. Well, at least they disclosed the vulnerability to the reset attack. They didn't seem to care that the phone reboots whenever you perform this attack against it. And it's not mentioned at all in the advisory. The reason this is so bad is that, first of all, it provides an attacker with a means to perform the device configuration disclosure stuff I talked about a minute ago. Also, TFTP is unauthenticated, so if you're able to own the local segment and you're doing some ARP poisoning, things like that, and you can tell the phone to reboot, you can then imitate the TFTP server and hand it your own configuration file, hand it your own firmware image, things like that. Cisco's mechanism for deciding whether or not it's going to download signed configuration files versus unsigned is whether or not there's a certificate authority essentially on the server. If you're imitating the server, you don't need to provide one. It'll go after the unsigned. So some tools to do this, obviously TCP kill from Long's tool suite. The vendor's response to this was that they addressed the issue in accordance with the IETF's recommendation, which basically tells you to challenge the reset by sending a reset ACK and then expect another reset. Really all that does is make the attack a little bit more difficult. TCP kill plows right through that. It doesn't really care. So the attack is slightly harder, but by much. Also, what Cisco needs to do is have the phones perform like they do if you perform an ICMP unreachable reset. They basically just reconnect the session. So it behaves slightly differently between an ICMP reset versus a spoofed reset, TCP reset attack. So the next one is a vendor called FiWin. This one's a little more recent than 2.5 years. They make a Wi-Fi phone that speaks SIP and Skype. They left the VxWorks debug console open, and this happens all the time. You wouldn't believe how many of these phones coming out have this enabled. So, in addition to that, they have a hard-coded username and password of 1 and 1. So, yeah, that's fun. Yeah, like I said, this is so, kind of indicative of the current VoIP. This kind of thing happens all the time. A lot of these vendors are just new to the market, new to this industry, and they don't lock down their devices before shipping. I personally don't focus too much on endpoint devices because there's another researcher named Sean who actually focuses almost entirely on endpoint devices, so I try to stay focusing on protocols and infrastructure and things like that. I think he's actually speaking at NoCon Name yesterday. Dropped a couple very similar to this. So basically you tell it to the device, you log in with 1 and 1, and at that point you've got VxWorks console access. You can look at RAM, you can format the disk, you can do whatever you want to do. It's wide open, essentially. So all you need to do this is a telnet client. So far there's been no vendor response, both to him and myself. We've both tried. There's so some things you can do if you happen to actually be using this phone to mitigate it. You can kind of fix the problem by disabling the console port. You log in and you issue this command, and it basically no longer lets you log in, but you can still connect to the port and see debug messages. So it's not a complete fix. Also, you can try updating the firmware, but this currently has some issues also. Now there's no updated firmware, and even if it were available, you can't load it on the phone because it requires a proprietary USB cable that you can only get from FiWin, and they don't sell it. So even if you were able to get firmware, right now you can't load it. So that's pretty much it for that particular attack. Next is the third and final section of my talk, where I'll be discussing some of the mitigation techniques that I talked about and what problems those have. No audio. That's okay. Basically, he's saying he's cleaned up his life. He's a better man, and this guy makes some offhanded snipe comment. So first, I'm going to talk about encrypting the media channel. That and encrypting the signaling channel are one of the ones that I hit on over and over again. So, right now, this was suggested in response to eavesdropping the media primarily. So, yes, there's a standard way to do this. It's called SRTP, which stands for Secure RTP. But right now, not that many devices yet really support it. There are a few. This is definitely moving in the right direction. But one of the reasons that not many devices support it is there's no standard way to negotiate or send the set for the media. There's a couple of different protocols proposals on the table, which is kind of hindering adoption, and people are waiting to see which one becomes the dominant one before they actually implement. There's the issue with this is even if you employ one of these ways to do it, it's done in the unencrypted signaling anyway. So it's kind of a moot point. If you can see the signaling and see all this being set up, you have the keys. So then you can just decrypt the media anyway. So one of those, I think it's called S descriptions, recently made it to RFC status. It's a little bit ahead of the others, but those also have their own problems, and I'm not going to get into that too much. Phil Zimmerman's come up with a modified version of SRTP called ZRTP, which does a Diffie-Hellman key exchange actually in the media channel. Personally, I think he's got it right. It's an excellent protocol. But the problem with that is it's not going to fly very well in the business space because of something that was mentioned in one of the Turbo Talks yesterday called CALIA. Basically, that's the Communications Assistance for Law Enforcement Act. And what it does is requires telcos to provide an easy and convenient way for the feds to tap your phone call if and when they need so. A lot of businesses are going to have to start complying with this, and ZRTP is encrypted end-to-end. There's no mechanism, as far as I'm aware, to tap the call midstream. So it's a great protocol, but I'm afraid it might not get a whole lot of adoption. And finally, you can wrap the entire thing in IPsec or TLS, which is what a lot of people do, but those both have their own problems. I'll talk about that in just a second. So the next one is encrypting the signaling. Basically, there's no standard way to do this yet. Basically, you can use TLS or IPsec, but IPsec tends to not be scalable very well for VoIP, and it also has issues with call setup times. In VoIP, like I said, it's very sensitive to latency and quality of service. If it takes 5 seconds for you to actually start talking to someone over the phone after they've picked up, that's pretty much unacceptable to a phone user. And TLS has its own issues. A lot of people have problems with it because it's not encrypted end-to-end. If one of the hops is compromised, you've got completely unencrypted signaling at that hop. And there's also issues with trust. There's no global PKI to kind of manage inter-network VoIP exchanges between, say, your VoIP provider and your buddy's VoIP provider. So, authenticating all signaling messages, I hit on that a lot too. In a lot of cases, this is going to require that the protocol be fixed. It also, the nature of VoIP kind of requires that some signaling has to be unauthenticated because you have to be able to initiate calls from untrusted parties. That's kind of the nature of phone systems in general. Whitelisting your known senders may work for you, but not for a call center or for a business. They have to receive unknown calls. And you can kind of band-aid the problem by wrapping the signaling in an authenticating protocol like IPsec or TLS, but I already mentioned the issues with those. So I touched on fixing the protocols here as well as earlier, so I'll talk about that next.
I was thinking maybe instead of houses.
And I also still don't have. Yeah.
It's better in a lot of ways.
That one's short, so I'll redo it.
I was maybe instead of houses we could live in teepees because it's better in a lot of ways.
Yeah, we should all live in teepees. So, fixing the protocols. There's really no immediate solution for that. It's kind of more consuming with open and standards-based protocols because you kind of have to convince the committee that there's a problem, and deliberation among them on what to do about it is going to take time. It may be a little faster or easier with proprietary protocols because you're talking directly to your vendor, but you still have to convince them that there's a problem. A lot of times they just want to turn a blind eye and not realize that there's an issue. So also I said don't trust caller ID. That's fine if you're a VoIP service provider or an automated system provider because you can implement that in your configuration. Unfortunately, that's not so good for end users because they've been trained since the early 90s or so when caller ID was introduced that the information that shows up on your phone is who's calling you. Okay, apparently I am out of time. I've got my 2 slides left, so I'm going to run through these. But that's it for that one. Unfortunately, there's no open source hard phone firmware as far as I'm aware. So that's pretty much out. You have to use your vendor's hard phone. And like I said earlier, demanding resilient devices doesn't really work very well. Rate limiting, low rate floods are still effective. It only takes one call setup message, a couple of seconds to make your phone ring constantly. The phone, but it's DOSing the user. And don't use TFTP or FTP. A lot of times there's no alternative. That's just what the vendors use, so you're kind of stuck there. So basically the overall VoIP landscape is fairly insecure. It's got a lot of fundamental protocol issues, and there's work being done to secure these things and fix these things, but the rapid adoption of VoIP and creation of new features, new phones, things like that, is far outpacing what's being done to secure them. And I don't have any time for Q&A. I'm out of time, but if you want to find me afterwards, I'll be happy to discuss with anyone. Thank you.